Hello and welcome back to G-Fun Facts Online. Today we are stripping away the surface of our planet to look at a phenomenon that is fundamentally rewriting the rules of marine ecology. For decades we have viewed the ocean as a buffer, a massive heat sink that absorbs 90% of the excess heat generated by anthropogenic climate change. But the ocean is no longer just a passive buffer. It is now experiencing its own version of wildfires. These are called marine heatwaves, or MHWs. These are discrete, prolonged periods of anomalously warm seawater that are causing mass die-offs, collapsing fisheries, and altering the biological fabric of Earth. In this episode, we are going to skip the fluff and dive straight into the comprehensive science, history, and future of these invisible fires. Let's start by defining exactly what we are dealing with. While atmospheric heat waves are visceral events we feel on our skin, marine heat waves occur beneath the surface, often invisible to the naked eye until it is too late. The scientific community needed a standardized way to track these events, and that came in 2016 with a landmark paper by Hobday and colleagues. They established a definition that allows for global comparison. A marine heat wave is defined as a period of at least 5 consecutive days, where ocean temperatures exceed the 90th percentile of the seasonally varying historical baseline, typically based on a 30-year climatology from 1983 to 2012. This definition is crucial because it accounts for season and location. It means a heat wave can technically occur in winter if the water is significantly warmer than what is normal for that specific time of year, allowing scientists to track these events in the freezing waters of the Arctic just as effectively as in the tropical Pacific. Much like hurricanes are rated from category 1 to 5, marine heat waves are classified by their intensity based on how far the temperature anomaly exceeds the local threshold. Category 1 is moderate, Category 2 is strong, Category 3 is severe, and Category 4 is extreme. To give you context, the infamous event known as the blob in the Northeast Pacific reached Category 4 status, signaling catastrophic potential. When scientists analyze these events, they look at 4 key metrics: intensity, which is the maximum temperature anomaly; duration, measuring how long the event lasts; spatial extent, covering the geographic area; and the rate of evolution, which tells us how quickly the heat ramps up. This rate is critical because it determines if species have any time to migrate or acclimatize. Now, let's look at the physical drivers. What causes the ocean to fever? It is rarely random. It is often a perfect storm of atmospheric and oceanic processes. The most common trigger, particularly in mid-latitudes, is atmospheric blocking, often called a heat dome. This happens when a high-pressure ridge parks itself over a patch of ocean, clearing the skies and allowing intense solar radiation to heat the water surface directly. Crucially, this high-pressure system suppresses surface winds. Wind is the ocean's primary way of cooling itself through evaporation and mixing warm surface water with cool deep water. Without wind, that heat accumulates in a stagnant, shallow layer at the top. This mechanism was the primary driver of the blob from 2013 to 2016. A massive ridge of high pressure over the Northeast Pacific, dubbed the ridiculously resilient ridge, deflected the jet stream and shielded the ocean from storms that would normally cool it down. Another major driver is ocean currents, which act as conveyor belts for heat. Western boundary currents, like the Gulf Stream in the Atlantic and the Kuroshio in the Pacific, carry warm tropical water toward the poles. If these currents meander or intensify, they can flood a temperate region with unexpectedly warm water. A prime example occurred off Western Australia in 2011, driven by the Ningaloo Niño. A massive surge of the Leeuwin Current, pushed by La Niña winds, transported record-breaking warm water south, triggering a Category 4 heat wave. We also have to consider teleconnections, the global web of climate patterns. The El Niño Southern Oscillation is the engine room for global marine heat waves. During an El Niño phase, trade winds weaken, allowing a massive pool of warm water to spread across the eastern and central Pacific, often triggering synchronous heat waves worldwide. Finally, there is the baseload of climate change. Anthropogenic global warming acts as a threat multiplier. As the baseline ocean temperature rises, it becomes much easier for natural variability to push temperatures past the extreme heat wave threshold. A weather event that might have been a mild warm spell 50 years ago now manifests as a severe marine heat wave because the starting point is already elevated. To understand the scale of this threat, we need to examine the historic inferno events that have defined this field. Let's look at the Mediterranean Sea, which is warming 20% faster than the global average. In 2003, coinciding with the deadly European terrestrial heat wave, the Mediterranean Sea surface temperatures soared 3 degrees Celsius above average. But it didn't stop there. Between 2015 and 2019, the Mediterranean experienced 5 consecutive years of widespread mass mortality events. These events affected 50 distinct groups of species across thousands of kilometers of coastline. We saw iconic species like the red gorgonian suffer tissue necrosis and death, effectively melting away and stripping the seascape of its complexity. Then there's the Western Australia event of 2011. Sea surface temperatures rose more than 5 degrees Celsius above average. This event is infamous for causing a regime shift. 100 kilometers of temperate kelp forests collapsed and were instantly replaced by tropical turf algae. Tropical fish species moved in and grazed on the new kelp recruits, preventing the forest from ever recovering. More than a decade later, the kelp is still gone. The ecosystem has fundamentally changed from a temperate reef to a tropicalized system. We discussed the blob earlier, but its biological impact was catastrophic on a different scale. Lasting from 2013 to 2016, it stretched from Mexico to Alaska. It caused hundreds of thousands of common murres to starve to death because their forage fish prey moved to deep water. It caused record numbers of humpback whales to become entangled in fishing gear because the heat wave pushed krill closer to shore, bringing whales into direct conflict with crab fisheries. It also triggered a massive bloom of toxic algae producing domoic acid, which shut down the Dungeness crab fishery. And of course, the Great Barrier Reef. The world's largest living structure has become the poster child for marine heat waves. Historically, bleaching events were rare, allowing reefs 10 to 15 years to recover. But the Great Barrier Reef suffered back-to-back bleaching in 2016 and 2017, again in 2020, 2022, and aerial surveys confirmed yet another mass bleaching event in early 2024. The frequency is now so high that many corals are killed before they reach sexual maturity, limiting the reef's ability to self-seed. This leads us directly into the ecological impacts, which can be described as a cascading collapse. The most severe impact is the loss of foundation species, the trees of the ocean. When corals bleach and die, the complex 3D structure collapses, leaving fish homeless. When kelp forests disintegrate due to cellular damage, we lose the entire ecosystem that depends on them. Seagrass meadows, which store vast amounts of blue carbon, are also vulnerable. In Shark Bay, Australia, the 2011 heatwave wiped out 36% of the seagrass, crashing populations of dugongs, sea turtles, and commercial scallops, and releasing stored carbon back into the atmosphere. We are also seeing mass mortality events among stationary animals. In the Mediterranean, sponges and bryozoans effectively melted, their tissues becoming necrotic. Because these animals grow slowly, recovery is measured in human generations. Even fish are not safe. In 2025, massive fish kills were reported in Western Australia due to thermal stress and oxygen depletion, as warm water holds less oxygen. Mobile species that can swim are fleeing the heat, leading to species range shifts and tropicalization. Commercially valuable species like cod and lobster are moving poleward, forcing fishers to travel further. Meanwhile, warm water herbivores like rabbitfish are invading temperate zones, decimating seaweed beds. In the Arctic, we are seeing Atlantification, where Atlantic species like haddock are moving into the Barents Sea and outcompeting true Arctic species like the polar cod. Heat waves also disrupt food webs by desynchronizing nature. Zooplankton bloom in response to temperature. If they bloom too early, juvenile fish that rely on them hatch into an empty pantry. This trophic mismatch can collapse an entire generation of fish. During the blob, the heat reduced the nutritional quality of zooplankton, which cascaded up to cause starvation events in sea lions, leaving pups emaciated on California beaches. The economic toll of these events is staggering. The ocean is an economic engine, and when it overheats, the gears grind to a halt. During the blob, the closure of the Dungeness crab fishery resulted in losses estimated at over $185 million. In the Bering Sea, the snow crab population collapsed by billions because the heat increased their metabolic rate, causing them to starve. In 2022, the fishery was closed for the first time in history, devastating Alaskan communities. Aquaculture has also hit hard. In 2016, a heat wave in Chile triggered an algal bloom that killed 27 million tons of farmed salmon, costing $800 million. Tourism takes a hit too. The Great Barrier Reef supports 64,000 jobs and contributes over $6 billion annually to the Australian economy. Recurrent bleaching generates negative headlines that threaten this entire sector. Culturally, for Indigenous communities, the loss of totem species and the threat to subsistence fishing represents a profound loss of heritage and food security. Looking to the future, climate models from CMIP6 paint a sobering picture. According to the IPCC, marine heat waves have already doubled in frequency since 1982. By 2100, under high-emission scenarios, they are projected to occur 50 times more often and become 10 times more intense. Events that currently last weeks could last for months or years. Perhaps the most alarming projection is the shift to a permanent heat wave state. By the mid to late 21st century, many parts of the ocean will reach a state where the average temperature is higher than the extreme heat wave threshold of the past. This implies that ecosystems as we know them will not persist. We are looking at a future of novel, heat-adapted ecosystems. The Arctic is warming 3 to 4 times faster than the rest of the planet, creating a feedback loop where melting sea ice exposes dark water that absorbs more heat. Warm water is now penetrating to the bottom, threatening benthic communities that have evolved in near-freezing stability. However, we are not helpless. Facing this existential threat, scientists and managers are developing urgent strategies for adaptation. We are moving toward dynamic ocean management. Traditional static fishing zones don't work in a changing climate. We need real-time data. Australia has deployed the Access S2 model to provide seasonal forecasts of marine heat waves, allowing managers to warn fisheries ahead of time. In California, the EcoCast tool predicts the location of target fish versus protected species based on ocean conditions, allowing for smarter fishing. Science is also intervening directly through assisted evolution. In the Red Sea's Gulf of Aqaba, scientists have found supercorals that are naturally resilient to heat. They are studying these genetic secrets to crossbreed heat-tolerant corals. In Fiji, the Reefs of Hope initiative identifies hot pockets where corals have survived and propagates them to reseed other reefs. We are also looking at nature-based solutions by identifying climate refugia, areas of the ocean that remain naturally cooler due to upwelling. Protecting these areas creates safe houses for marine life to survive and eventually repopulate surrounding waters. Fisheries are adapting by diversifying, holding portfolios of permits for both cold and warm water species to ensure against stock collapses. To conclude, marine heat waves are no longer a theoretical risk. They are a dominant force shaping the modern ocean. The physics are simple. As long as we pump greenhouse gases into the atmosphere, these invisible fires will burn hotter, longer, and deeper. While mitigation is the only way to stop the warming at its source, adaptation offers a lifeline. The era of the stable ocean is over. We are now the stewards of a fevered planet, and our actions today will determine what life remains in the seas of tomorrow. Thank you for listening to G Fun Facts Online.